Okay, good morning. So today what I'd like to do is to talk about calorimetry. Okay, so we've done a little introduction into energy, kinetic, and potential. Now we're going to talk about calorimetry, which is section 5.4. And this is the nuts and bolts of essentially how we measure heat. And that's really what calorimetry, the word means, measuring heat. Okay, and the idea is essentially based on this important principle, which is that if you have matter that has a higher temperature than another piece of matter that it's in contact with, so right, they have to be in contact with each other in some way, which we call thermal connection, then what happens is energy flows from the hotter object to the colder. So energy flows in that direction. Okay. It essentially occurs through collisions. Objects that are hotter, the velocities of the particles are faster. They're higher velocities than in the colder material. So there's just a bunch of, countless collisions occurring at the surface where they connect with each other. So these ones are moving fast, these ones are moving slow, and then when they collide with each other, the ones that were moving slow are now moving faster, and the ones that were moving faster now moving slower, until they finally reach the same speeds, the same speed distribution. And so then the energy flow stops, and there's no longer energy flowing. And so that, if you recall back at the beginning of the week, what I said was that the energy associated, the energy transfer associated with a difference in temperature. So if there's a difference in temperature and energy is associated with that, we call that heat. So, it's not probably worth a reminder. Heat, we'll use the symbol Q, is the energy that is transferred from two objects at different temperatures. So if they're at the same temperature, then we wouldn't expect any heat to flow. But if they're at different temperatures, then we would expect heat to flow. Okay. In general, the heat flows from the hot to the cold region, right? But not the other way around. In order to make it go the other way around, you have to use a heat pump. You have to essentially use an air conditioner or a refrigerator. So you have to use energy to make it go the other direction. But in general, the spontaneous or the natural course of events is that the energy flows from the hot to the cold. Okay, so that's called heat. Right? At one time, it was believed that heat was actually a thing, like there's something in the material called heat, and we could actually look for heat particles, but there are no such things. It's not an actual material. It's just the relationship between the particles in one region, the particles in the other. The ones in the hot region are moving faster. The ones in the cold region are moving slower. They collide with each other. And when they collide with each other, there's a, evening out, right? So eventually they're all moving about the same speed. And so they're at the same temperature. So temperature is really, what is temperature? So temperature is a measure of the kinetic energy of these particles or these objects. Okay, so all these particles in here are moving around. Temperature is a measure of how fast they're moving. So the faster they're moving, the higher the temperature. Likewise, over here, they're moving, maybe not moving as fast on average, but they're still moving around. And if they're moving, then they have a temperature. So the faster things move, the higher the temperature is. And we'll look at that a little bit more when we get to chapter 10. Okay. What I'd like to do now is to show you what we'll call a constant pressure calorimeter. And that's the calorimeter, essentially the model for the calorimeter that we're going to use for this discussion. So this is called a constant pressure calorimeter, or a coffee cup calorimeter. You can actually make it very simply just using a couple of coffee cups. So you take 2 coffee cups. They're really styrofoam cups, not really coffee cups. They're styrofoam cups. You put one in the inside and one in the outside. You stack them. And styrofoam is a pretty good insulator because it's mostly air. And then you put a little cork in it, and inside the cork you put a little stirrer, right? So it's like a little, it's got that little ring down at the bottom. That's so you can stir the liquid to make sure everything's distributed evenly. And then you can also put a thermometer into the liquid. Okay, so there's a thermometer that's measuring the temperature, and the stirrer is mixing things up. And then, you know, at some point you have to open it up and put reactants in. So since this appears to be occurring in water, right? That blue liquid down there is water. This is an aqueous reaction like we covered in chapter 4. We looked at precipitation, we looked at oxidation reduction, and we looked at acid base. So this could be one of those types of reactions, okay? Now, in general, precipitation reactions are not really associated with much heat transfer. They just are not particularly energetic. So if you're trying to measure heat of reaction from a precipitation reaction, you get a pretty small number. It's not going to be all that much. Acid-base reactions can produce some heat, though. Actually, acid-base can. Depends on the concentrations of the acids and the bases, and it depends on which acids and bases we're talking about. In general, the strong acids with strong bases are the most energetic of these reactions. Some acid-base reactions are endothermic. They actually absorb heat. So the solution gets colder, or actually I should say the water gets colder. Some reactions, some acid-base reactions are exothermic. So the strong acid with a strong base is typically exothermic. And so the water will get hotter because the reaction is releasing heat into the water, and the water will get hotter, okay? So that thermometer is essential to this process. The thermometer is a measure of temperature. And we're going to use the measure of temperature to measure the amount of heat that's being released. And we'll go through that calculation in a moment. Okay. I do want to point out that there is something called a constant volume calorimeter. And I'm going to see if I can bring this up for you. Yeah, here it is. Okay. So this is called a constant volume calorimeter. Let me just see if I can find it. It's an image on a website. There it is. Okay, so let me share. Okay, there it pops up. Okay, so that's a constant volume. So this is a little different situation. So if you take a look at this device, it's a little bit more sophisticated, right, than the previous one, the constant pressure. And, you know, this one is used for various types of reactions that we might be studying. The constant volume calorimeter, it has a stirrer in there, but this one it's motorized, right? It has ignition wires. So it actually has an electrical circuit going through it. It has a thermometer. Notice the thermometer is in the water, okay? And that's called a water bath. So the water is called a water bath. Inside the water bath is what they call the sealed bomb. So not like a bomb, like an explosion, but the bomb is a device to do combustion. So this device is made for combustion. Now, if you think about it, if you're combusting something, it's burning. Combustion generally requires a little more sophistication because you're burning something. So inside there is the sealed bomb has high pressure oxygen that's been put in there. This picture doesn't really show you how they get the oxygen in there, but there's usually a little tube, you know, a metal tube that's connected to it that you can open and close just to fill it with oxygen. So very high pressure oxygen, maybe 30 atmospheres of oxygen in there. pure oxygen, just to make it burn very rapidly and very well. And then there's a sample cup. That sample cup typically has, you know, it's just like a little piece of metal and like a little cup. And above it, the wires are going through a solid sample. So the solid sample could be aspirin. You know, think of like a little aspirin tablet or ibuprofen or something like that, or sugar. It could be like a little, like a sugar cube, something like that. So it's an organic reaction, right? It's a combustion, which is a redox reaction of an organic compound like sugar or you know, aspirin, something like that. So the oxygen at high pressure reacts. So how do you get the reaction to start? Well, that's where the ignition wires come in. The ignition wires go through the sample. So there's actually, typically you actually just thread the wire through the sample. And then you attach the ignition wires on the outside up at the top. You attach them to some high voltage supply, 100 volts or 200 volts or something like that. You hit the switch, which applies the voltage to the wires. And then what happens is that produces enough heat in the wires to ignite the reaction. Now, it might not ignite in air because there's just not enough oxygen in air, but in that high pressure oxygen, the reaction will ignite. And you'll get a very rapid combustion. Less than a second, this sample will combust. And then what happens? Combustion is exothermic. So if a reaction is exothermic, it releases energy, it releases heat into the surroundings. The surroundings are actually this oxygen here. And then the oxygen molecules that didn't react will collide with this metal container. And then when that collisions occur, the heat will transfer through the metal and then into the water. And it happens relatively quickly, within a minute, 30 seconds. And then suddenly the temperature will start rising. So just like the constant pressure calorimeter, you're measuring the temperature change in order to figure out how much heat is released, okay? So this is constant volume. This is what we would use if, the pressure is not constant, so the pressure changes. So if the pressure is not constant, then generally we're not going to use enthalpy in our calculations. We're going to use internal energy. We'll use delta E. But if we're interested in enthalpy, we're generally going to want to use constant pressure. So that's where we'll use the, this calorimeter, this little styrofoam calorimeter. You can do it more sophisticated than styrofoam cups, but not much. It doesn't need to be much more sophisticated than that. Okay. Now this is constant pressure because this cork here is not really sealed in. It's not screwed in or anything. So air can actually go back and forth. And so if the pressure changes here, the pressure will push the cup up a little bit, and then some air will either escape or come in, and it'll keep the pressure constant as what the pressure is outside. The external pressure is atmospheric pressure. So that'll keep the pressure in there constant. And what we said in our discussion of enthalpy yesterday is that, you may not have watched that video yet, but the enthalpy requires that the pressure be constant. So this device is better used for figuring out enthalpy. This device over here is better used for determining the internal energy change. Okay, so there you go. All right, so let's come up to an Alex problem. And let me just go over to here. Okay. Oops. Did that work? Okay, let me share again. There we go. All right. So there's the first Alex problem. It says calculating the specific heat capacity. So let's talk about specific heat capacity. Before I give you a little mini lecture on that, I want to show you, let's just look at this question and look at the kind of information it's giving. A chemist carefully measures the amount of heat, right? So heat, Q is heat, right? Needed to raise the temperature of a 697.0 milligram sample of a pure substance. So they're not telling us what it is. It's a pure substance though. So notice that's mass, right? So mass is an important part of this problem. Mass, heat, and then see how the temperature changes from 26.3 to 37.3 degrees Celsius. So that's like a warm day. That's like 80 degrees or something like that. And then this is pretty close to metabolic temperature, so like 98.6 degrees Fahrenheit. So there's a temperature change. So temperature change is important too, okay? So and then in fact, they actually tell you how much heat. They tell you the heat is 32 joules, right? So there's a relationship between heat, Q, mass, M, and temperature change, delta T. And the relationship is called the specific heat capacity, which is a pretty long name for something, specific heat capacity. So in general, people usually call it specific heat for short. And the specific heat is, or specific heat capacity is what we're going to look at. If you take more advanced chemistry courses, you'll mainly be looking at heat capacities. But in general chemistry, we're concerned with the specific heat capacity. So we'll come back to that problem, but I want to talk to you a little bit about specific heat here. So let me put in here specific heat. So here's what we know. Sorry, computer's giving me lots of little warnings here. So here's what we know. Heat transfer, right? I'm going to call it heat transfer because that's really what heat is. It's a transfer of energy, right? Energy is going from one spot to another. Okay. Think of the sun, right? The sun is transferring heat from itself to the earth. That's a heat transfer. Okay. So heat transfer, the amount, is proportional to the difference in temperatures between the two regions that we're looking at, right? So in other words, if I have two objects, and this one's at some temperature and this is at some other temperature, the amount of heat that flows, okay, we're assuming that the second region is lower in temperature, the amount of heat that flows depends on how different those two temperatures are. So if the difference in temperature is very small, like let's say they're almost exactly the same temperature, you're only going to get a little bit of heat flow, right? But if it's a big temperature difference, one of them's 100 degrees C and the other one's 10,000 degrees C, you're going to get a lot of heat flow, right? So the amount of heat is directly proportional to the difference in those two temperatures, okay? Now here's another thing that it's proportional to. It's also proportional to the mass of the object that we're looking at. This is the mass. All right, so here's what I mean by that. Imagine that you have a gigantic bathtub, right, with a lot of water in it, right? There's 50 or 100 gallons of water in there, okay? And let's say that water is really hot. 75, that's too hot to get in, right? That's going to boil you. You're going to be in trouble if you get in that water. It's going to be transferring heat into the air, right? Heat is going to be flowing into the air because the air is only around 20 degrees C. That's about room temperature. There's going to be a lot of heat flowing. Now, one of the reasons a lot of heat is flowing is because there's a big temperature difference, right? That's not a small temperature difference, right? But the other reason is there's a lot of water. That mass of that water is very large. So compare that. Compare that to like a tiny little cup of water, a little cup of water. And this one's at 75 degrees C. It's still going to transfer heat into the surroundings, right? Because the water is much hotter than the air. But the amount of heat is not going to be nearly as much as here. The amount of heat depends on how much substance you have. The Earth transfers a lot more heat into space than I do, even though my average temperature is greater than the average temperature of the Earth. The average temperature of the Earth is actually around, I think it's around 60 degrees Fahrenheit. So it's like 15 degrees Celsius or something like that, right? I'm much hotter than the Earth. I'm 37 degrees C or 98.6 degrees Fahrenheit. So, the temperature difference between me and space is much greater than the Earth and space. However, the Earth transfers a lot more heat to space than I do but that's mainly because of its mass. The mass is an important aspect of that too. Okay, so what we see here is that the amount of heat transfer is proportional to the temperature difference. It's also proportional to the mass, but it's not equal, right? Temperature and mass cannot be equal to heat. These are different quantities. So how do you make things equal? In sciences or in arithmetic, in mathematics, this is what we do. The way you turn a proportionality into an equation is you just put in some constant. So the constant, I'm going to use C for constant, right? Well, actually the C is capacity. That's why we use the symbols. Capacity starts with a C. But just think of it as constant. So you put a constant in there, and if then you multiply that constant by our two proportional variables, right? Then you get an equation. So this is no longer a proportionality. It allows you to actually calculate one from the other, right? So for example, if I said, hey, here's your mass, here's your change in temperature, what's the heat? I can't calculate that there. I know that more mass gives me more heat, but I can't actually figure out the amount of heat. You can't calculate it. But if you put in this proportionality, that now allows you to figure out the relationship, the actual numbers. But you got to know what that proportionality is, right? You got to know what that actual constant is. You got to know its value, right? So one of the tricks here is, how do you figure out what the actual value of the constant is? Well, that's what people have done over the last 150 years. They've done experiments to figure out what these values are. So I'm not going to go into detail about how you figure it out. In general, what you do is you use a really nice thermometer so that you can measure temperature very well. You use a nice balance so that you can measure the mass really well. So you know those really well. The trick here is, how do you figure out Q? And just to give you like a little insight into it, what you generally do is you use electricity. Electricity, you can measure electricity really well. If you think about your phone that you have, it's a marvel of electronic technology. There's all kinds of circuits in there where voltages are being regulated and controlled and measured and changed at very precise degrees. So our development of electrical or electronic technology is so impressive. And part of it's just because the nature of it, you can do that, is that you can measure electrical energy really well. You can measure it down to 0.001% pretty easily, right? And so what that allows you to do is to measure energy really well. Well, if you can measure energy really well, heat is energy, right? It's the amount of energy being transferred. So essentially you put in a certain amount of electrical energy, that energy gets converted into heat, and you know how much electrical energy went in, so you know the amount of heat that went in. So that allows you to measure this one really well. So if you know this, and you know this, and you know this, then you can just say, hey, I can figure this one out now. C is just going to be Q over M delta T. And so now I measure these ones, and now I've got this. And that's essentially what you do. Once you've got this, now you can use it in this equation to find Q in any situation, right? You don't have to have this electronic measurement in order to figure out what Q is. You now know what this one is. You can measure the mass and the temperature difference, and then that'll give you Q in the future, right? So the first problem that we're looking at is kind of getting at that point, which is, if I use electronic technology to figure out Q, and I measure the mass really well, and I measure the temperature change really well, can you figure out the value of this C, which is called the specific heat capacity? Okay. So what I'm going to do is let's take a look at the problem now. This is the same one I was just looking at a moment ago. So let me just put a new slide up here. So in this problem, they tell you, hey, you want to find Q. They tell you to find the mass. I'm sorry, to find the heat. Oh, actually, let me rephrase that. Okay. They tell you that you carefully measure the heat to raise the temperature of 697 milligrams. Okay, so let's go back. Let's take a look at this so you can see it. So a chemist carefully measures the amount of heat needed to raise the temperature of 697.0 milligrams of a sample of a pure substance. The pure substance is an important statement because it turns out the heat capacity is different for different materials. Each type of material has its own specific heat capacity. Water has a value, alcohols have values, wood has a value, metal, each metal has a value. And if you mix materials, then you get a mixture, and there's no easy way to figure out what the actual value is without actually measuring it itself. So each material has its own specific heat capacity. So they tell you it's a pure substance. The temperatures are given, and then it says, hey, the amount of heat is 32.0 joules. What can the chemist report for the specific heat capacity of the substance, rounded to 3 significant digits? So let's take a look here. Let me stop share this one. And I'm just going to write down our numbers here. Let's just write down our numbers that we have here. So the first number that's given is 697.0 milligrams. Well, that's a mass, right? That's mass. So that's your mass. The next thing it says is the temperature goes from 26.3 degrees C to 37.3 degrees C. So that's your delta T, right? That's your change in temperature. Now, we'll go over what the numbers are in a moment. And then it says the experiment shows that 32.0 joules of heat is actually required to do this. What is the specific heat capacity? Okay. Well, I'm going to start with the original equation again. Heat transfer is equal to the, I'm going to put the mass first. It doesn't really matter which one you put first, but I'm going to put mass first because most of the time that's what people do historically. There's actually an argument for putting C first. It kind of makes sense to put C first, but just historically, chemists will put the mass first. Okay, so MC delta T. Now, we want to find C. We want to find the specific heat capacity, so that would be Q over M delta T. Okay. So what I'm going to do is I'm just going to put the numbers in, and we'll go over what the units are. And then we'll take a look at that. The units are important. The mass is 697 milligrams. And yes, that's going to need to be in grams, but I'll leave it in milligrams for now. Now, how do we find the delta T? Delta T is final minus initial. T2 minus T1. So if something is going from this to this would be the final. This would be T2. And it's coming from this, so that would be T1. So it looks like it's 37.3 degrees C minus 26.3 degrees C, right? So now you can do your arithmetic. Just grab my calculator here. Let's get a little calculator. There you go. Okay. So 32.0 divided by 697 divided by, and then I'm going to put this in parentheses, 37.3 minus 26.3, which is, I think, 11 degrees, right? Close parentheses. And you get a small number. C is 0.00417. That's 3 sig figs. Joules per milligram degrees C. Now, why is it milligram degrees C? You got milligrams down here, and then you've also got degrees C down there. So per milligram per degree C. These are unusual units. Typically, you want to have this either in grams or kilograms. Chemists are most likely going to put it in grams. If you're taking physics, they'll put it in kilograms. Some people put it in moles. Actually, putting it in moles it makes sense, but this is the specific heat, and specific usually means divided by mass. So that's why it's per gram, but not milligrams. Don't put milligrams or micrograms or nanograms or picograms or megagrams or gigograms. Typically you're going to want to have it in grams. So how do we do that conversion? I wanted to put this off until this step because it's you could have done it at the beginning, which is fine, but I want to show you that you can actually do it now. A milligram is 10 to the minus 3 grams. We want to get rid of the milligram and replace it with grams. So what I'm going to do is I'm going to put the milligram up here, right? If I put this one up here, now the milligrams are going to cancel. And then you put 10 to the minus 3 grams down here. And then that will give you joules per gram degrees C. It's usually written gram degrees C, not degrees C, grams. Okay. So you're dividing by 10 to the minus 3. You can do that on your calculator. That's fine. Dividing by 10 to the minus 3 is like multiplying by 10 to the 3, right? So if I say 1 over 10 to the minus 3, that's the same as 1 times 10 to the plus 3. You just change the sign to bring it up. Now that makes more, that's easier to do in your head, right? Like if I say dividing by 0.001, what do you do? Well, let's put it this way. I'm going to multiply it by 1,000. Now you can kind of tell what to do. So you're just going to take your number and multiply by 1,000 and you get 4.17, right? Because you're going to move it 3 places, 1, 2, 3, and you get your 4.17. So there you go. There you go. Now that's a reasonable, that's water. Oh my goodness, that's water. Water is 4.184. So that is really close to water. So that tells you that you're talking about water for the specific heat capacity. Okay. And there you go. So Q equals MC delta T. We could, many textbooks will have various different types of problems. They'll say, hey, here's the mass, here's the specific heat, here's the heat, what's delta T? Or here's the initial temperature, but not the final temperature, find the final temperature. There's all kinds of things. Is that right? Did it actually say that? Let me take a look. So Abdallah, that's a good question. I didn't, because in the one that I'm looking at, it doesn't actually tell you what they want the units to be in. So is that right? No, I think they wanted it per gram. I think they wanted it grams. But you know what? There's actually another issue that comes into play here that I want to mention, which is looking at the solution on Alex. They do a little tricky here with the temperature units. So I'm glad you brought that up because that made me look at the example. So there's an issue here with how they do the temperature units. Oops, sorry. So the grams are fine. What you'll see when they do it is they put the temperature units in Kelvin. Okay. So let me just talk a little bit about Kelvin. Typically, we don't talk about Kelvin in this course until we get to chapter 10, which is the next chapter. But whoever wrote these problems, they were writing it from the perspective that you cover chapter 10 first. In some textbooks, chapter 10 is chapter 5, and chapter 5 is chapter 6. So the order gets shifted, but it's not a big deal. Let me just show you the deal. So the temperature scale that we've been using is called the Celsius scale. Okay, and our symbol is degrees C, right? So this is essentially based on water. So water freezes at 0 degrees C. Water boils at 100 degrees C, right? So that means that, in between there is like room temperature. Room temperature is typically around 20 degrees C. Sometimes people put as 20 or 25. And then metabolic temperature in there is also, right? So the human body temperature, 37 degrees C, right? So that's called the Celsius scale. There is a second scale that we're concerned with, and this will be important in the next chapter. It's called the Kelvin scale. And it's K is the symbol for the unit. These are the unit symbols right there. So you can write the Celsius as T degrees C, right? So that means we're giving the temperature in degrees Celsius, or the Celsius scale. Or you can have the Kelvin scale, T sub K, right? Now, the relationship between these two scales is very simple. The Kelvin scale, if you want to know what the temperature in Kelvin is, it's just the temperature in Celsius plus 273.15. Okay. So all you have to do to get it into the Kelvin scale is add 273.15. Most of the time when we deal with gases, we're going to use this scale. We're going to use the Kelvin scale. But in thermochemistry, people still use the Celsius scale. And that's perfectly fine. We can use either in the Celsius scale. So here's what happens. Suppose my initial temperature, so T1, is 26.3 degrees C, and my T2 is 37.3 degrees C. Delta T would be 37.3 minus 26.3, and you'd get 11.0 degrees C, right? Makes sense. What happens with the Kelvin scale? Well, if we're going to do it in the Kelvin scale, we've got to change these numbers. So your T1 would not be 26.3. It'd be 26.3 plus 273.15, right? So 273.15 is 299.45 Kelvin, right? Just adding 273.15. What about T2? Well, that would be 37.3 plus 273.15. So you're just going to add 11 to it. So it's going to be 310.45 Kelvin. Okay? Hopefully that makes sense. Now, let's calculate delta T for this. Delta T, again, it's just T2 minus T1. So that would be 310.45 minus 299.45. And guess what you get when you do that? You get 11.0 Kelvin. You get exactly the same number here as we had here, just with different units. Okay? So what you can do when you do this problem is just leave it in Celsius. You're going to get the same answers you would in Kelvin, because when you're looking at differences, these two cancel each other, right? You're adding this, but then you're taking the difference, so you're subtracting it, and so it disappears, the big difference. So you get the same number. So in this particular problem, they're going to have joules, that's your energy units, Q, divided by G for grams, not milligrams, but grams. And then they're going to have a capital K, an uppercase K, which is telling you that this is in Kelvin. And then this is in grams, okay? Not to be confused with this. You could have joules per kilograms Kelvin, or joules per kilogram Celsius, degrees Celsius. You could have that too, right? So here the K is referring to kilo. Here the K is referring to Kelvin. Uppercase is Kelvin, all right? So when you're doing kilograms, try to avoid doing this. You're going to see it out there. People do this, but that's confusing in a sense, right? Or even this, right? kg. This is confusing. What's that K referring to? Is it referring to kilo, or is it referring to Kelvin? It's not clear. So if you use a lowercase k, that's kilo. Uppercase K is Kelvin. In fact, you could even have the unit Kelvin, right? Kilo Kelvin's possible because you got your prefix with your unit. So kilo actually sounds pretty cool. How many kilokelvins was that? And you will hear Kelvin in science fiction. So if you watch science fiction shows that are based on the Earth, right? So Star Trek, for example, not Star Wars, because Star Wars, they're in a different galaxy. So none of the units there are the same as here. But if you're, I guess Star Trek is probably the most one. You're going to hear Kelvin. Kelvin is common because it's actually the technical unit of temperature that engineers prefer to use compared to Celsius in any case. Okay, so good. Thanks you, Abdallah. That was helpful that you put that up there. Okay. All right, so let's take a look at the next one. The next problem is very similar. Very, very similar. So let me come over here. Okay, next problem. Calculate the energy required to heat. So energy required to heat, the meaning of that is that you can use energy to heat things, right? So you can use electrical energy to heat things, right? So I can take electrical energy, put that through a piece of wire that's been turned into like a spring, and as the electrical current runs through the wire, there's friction. The electrons are bumping off of each other, and there's a loss of energy, and it gets converted into heat. So electrical energy can be converted into heat. Work can be converted into heat. Chemical energy can be converted. So there's many different ways you can get heat out of stuff, right? In fact, the sad truth of it is our universe is going to, over time, going to die as everything gets converted into heat. It's going to be more and more difficult to use that, but that you don't have to worry about that. We'll long be dead by then. So in any case, calculate the energy required to heat 187.0 grams of aluminum. Aluminum is a pure substance, an element, from 0.8 degrees Celsius to 18.5 degrees Celsius. Assume the specific heat capacity of aluminum under these conditions is not 903 joules per gram per Kelvin. So that's joules divided by grams divided by Kelvin. When you have the -1, that's divided by. Round your answer to 3 significant digits. So this is very simple. This is just like the one we did. It's just that instead of asking for the specific heat capacity, we are being asked to find the amount of heat, the amount of energy, right? They're not telling us how they got this energy, but in any case, it's heat. Okay, hopefully that one makes sense. So let's take a look at it. Yeah, these are fun. These are fun problems, actually. These are ones I actually got right when I took chemistry. Let's take a look. 187.0 grams of aluminum. So aluminum, okay, goes from 0.8 degrees C to 18.5 degrees C. And assuming the specific heat capacity, so specific heat capacity is decimal 903 joules per gram per Kelvin, right? -1, -1. Right, and I hope you understand that, right? Because if I say 1 over x, I can write this as x to the -1, right? 1 over x squared would be written as x to the -2. So based on that logic, 1 over grams is grams to the -1, and 1 over Kelvin is Kelvin to the -1. So that's what we're doing here, okay? All right, so we pretty much got everything. This is C, this is delta T, and then this is M, and we want Q. So here we don't even have to change the equation at all. By the way, you'll in your textbook, if you're reading the textbook, they actually use the symbol S instead of C for specific heat. And then they put the M after the S, and then they put the delta T. So you may see it in that form too. But in any case, here we go. So our mass is 187 grams. It's in grams, so that should be okay. The specific heat capacity is decimal 903. Oops, I almost put degrees C. And then we got to do our delta T. Now that, oh, remember, delta T in Kelvin is the same as delta T in Celsius. All right, so that's the key. I could go through and show it to you, but you could do it yourself, right? So all you got to do is figure out in Celsius and make it in Kelvin for changes in temperature, okay? Delta T, not each specific temperature would be different, but the difference would be the same. So if you look at this difference from this to this, it's 18.5 minus 0.8. So what is that? Is that 17.7, I think? 17.7 Kelvin. I'm just going to put Kelvin in there. Okay. That way your Kelvins cancel and your grams cancel and you've got joules. So Q is going to be joules. Let's estimate it. I'm just going to do a rough estimate in my head. 187. So that's like 200. This is like pretty close to 1. So 200 times 1 is 200. And then this is like close to 20. So 200 times 20 would be 4,000. So it's going to be, you know, around 4,000. It's less than that. It's probably like 3,520 or something like that, right? But let's see. 187 times 0.903 times 17.7, a little under 3,000. Oh, I was off. How did I get 200? Wow, I guess my rounding was pretty bad. 200 times 1 would be 200 times 20 would be 4,000. It's actually closer to 3,000, so I was off a little bit. My rounding wasn't very good. Let me just check it again. 187 times 0.903 times 17.7. Yeah, it's closer to 3,000. To 3 sig figs, I'm going to put it in scientific notation. So here's the number I get. 2988.84. 2988.84. Yeah, there we go. So now I'm going to do it in scientific notation. Move it 1, 2, 3. So that's 2.98884. Yeah, 3/8. And then I moved it 3. So times 10 to the 3. Now we can round it. 1, 2, 3. This number is 5 or greater, so this gets rounded up. So 2.99 times 10 to the 3 joules. Okay. Now that's a big enough number. You could also substitute kilojoules. I don't think they do that, do they? Do they do kilojoules in this one? Oh, they do it in kilojoules. Okay. So that's okay. You can do kilojoules. That's not a problem. So if it's in kilojoules, if they want it in kilojoules, remember kilo's 1,000, right? 1 kilojoule is 10 to the 3 joules. So just do the conversion. 2.99 times 10 to the 3 joules. 1 kilojoule is 10 to the 3 joules. Your 10 to the 3 cancel, and you get 2.99 kilojoules. And there you go. Okay. That one's not too bad. Once you get the first one, this one's not bad at all. All right, let's take a look. Okay, so be aware when you do these problems, especially when you take your test, sometimes they're going to want the units to be in joules. Sometimes they're going to want it to be in kilojoules. I don't expect them to have many problems where they want it in millijoules or microjoules or anything like that. But joules and kilojoules are pretty common. Those are the 2 most common units. Okay. Okay, so let's take a look at next one. Using the specific heat capacity to find temperature change. So now we're going to find delta T, right? So we're just going to take that same equation and find delta T. So a chemical reaction takes place inside a flask, submerged in a water bath. The water bath contains 8.80 kilograms of water at 37.1 degrees Celsius. During the reaction, 102 decimal kilojoules of heat flows out of the flask and into the bath. Calculate the new temperature of the water bath. You can assume the specific heat capacity of the water under these conditions is 4.18 joules times grams to the -1 times Kelvin to the -1. Round your answer to 3 significant digits. Okay, So mass of the water is given, the amount of heat is given, the specific heat capacity is given, the initial temperature is given, and we're essentially asked to find the new temperature, which would be the final temperature of this, right? But it's really the same thing. Anytime you see heat and temperature, you know, specific heat's given in there, you're going to be using that equation. So let's take a look at this one. Okay, so I'm going to write our primary equation here, mc delta T. Okay, but I'm going to expand the delta T. It's actually mc times T2 minus T1. Final minus initial, right? And let's do a little algebra here. What they're asking us for is the new temperature. That's the final temperature. That's your new temperature. So if you're asked for that, how do we deal with this algebraically? We have to be careful, right? First step could be to divide both sides. We don't need this middle part. But actually, why not? We could do that. Divide all three, right? We could divide everything by MC. Right? So now M divided by M is 1. C divided by C is 1. Okay. M divided by M is 1. C divided by C is 1. But we want to find T2, so we don't really need this middle part. We don't need to find delta T. We just need the beginning and the end right there. So let me just bring this down as Q divided by MC, right? So I'm just bringing this down. And that's going to be equal to T2 minus T1. Okay. So we want to find the new temperature, which is T1. So add T1 to both sides. Right? Because if you add T1 to both sides, minus T1 plus T1 is 0. So you get Q over MC plus T1 is equal to T2. So now you've got everything. Again, the units are going to be an issue. For this one, actually, I guess we got to have everything in Kelvin, right? But that's fine. It should work out fine. You know, it's not like they're going to ask for it in Celsius. Oh, actually, no, they gave it to us in Celsius. Whatever. Okay, so the amount of heat is 102. So the heat is 102 kilojoules. The specific heat capacity is 4.18 joules gram to the minus 1, Kelvin to the minus 1. T1 is 37.1 degrees Celsius. Okay. All right. Okay. Actually, I'm going to show you a way to do this pretty easily. So you've got 102 kilojoules. Now, there's an issue here. See that kilo? That's a problem. I'm doing the first term. So your mass was, I'm sorry, I didn't write down the mass. The mass was 8. Oh, actually the mass, oh, good. 8.80 kilograms. Oh, good. That actually simplifies things. Okay, I didn't write that down. So your mass is 8.80 kilograms. Take a look at what happens here. The kilos cancel. So no need to do any kilo conversions because there's a kilo in both of them. That's nice. So now you got joules per gram. And then you got to divide that by the specific heat capacity, which is 4.18. And that's joules. I'm going to write it, I guess I'll write it this way. Divided by grams degrees C. Okay, see how I put it in grams degrees C, even though they put it in grams per degree Kelvin? Grams, joules per gram Kelvin. I'm going to put Celsius, it's the same. The specific heat capacity is the same in either unit. Okay. So now what happens is some of these units are going to cancel. The joules cancel, the grams cancel. And then you've got 1 divided by 1 over Celsius, which is Celsius. Okay. Now you can just add your 37.1. And that'll give you your final. All right. So sorry, but I'm running out of room here. Okay. So you can interchange the Celsius. Now, if you want, I mean, but the problem is if you put this into Kelvin, that's going to give you an answer in Kelvin, and then you got to subtract it to get it back to Celsius. So just take a look at what units they want. 102 divided by 8.80 divided by 4.18. So that first term you get 2.77, and that's actually your delta T, right? Delta T is Q over MC. So that 2.77 that you're going to get here, that 2.7, that's your delta T. That's how much it's going to go up by. So you start at 37.1, it goes up by 2.77. So add 37.1, round it, and you get 39.8. 39.9, sorry. 39.9. And that's degrees Celsius. Okay. I don't think they're going to want this one in Kelvin because the first temperature was in Celsius. Yeah, it's 39.9 Celsius. Okay. That's not too bad. All right. So be careful. Like it's perfectly fine if you get rid of the kilos. This would be 102,000. This would be 8,800 in grams and joules. You got rid of the kilos, right? But you don't really have to get rid of the kilos here because they cancel each other. So you can save yourself a couple steps. It'll still work if you just, it'd be a problem if you did one but not the other. But if you can't, if you converted each of them to joules and grams, it would still give you the same answer because the thousands would cancel out. Okay. So if you coming back, this is what it looked like, right? Q over MC plus T1 equals T2, right? And the reason for that is that Q over MC is equal to T2 minus T1, right? That delta T, that's your delta T right there. So if you add T1 to both sides, that's just going to give you T2. And there's your answer. And that's what we did. Oh, sorry, plus T1. We did this term, we added the T1, and that gave us the T2. All right, so that's really, actually, all three of those problems are pretty similar. They're using the same equation. You're just manipulating each one a little differently. Okay. All right. Let's take a look at this one. So this one's called calculating the molar heat capacity. So molar heat capacity, that term molar, remember molarity? Molar heat capacity, this is involving moles. Okay, so there's specific heat capacity and then there's molar heat capacity. Okay, so a chemist carefully measures the amount of heat needed to raise the temperature of 610.0 milligrams of a sample of C3H9N. What is C3H9N? Propylamine, maybe? Might be propylamine. C3H9. Have to get an organic chemist out here to tell us what that is. Okay. It's probably propylamine. From 0.2 to 14.1. So again, you're seeing mass. You're seeing change in temperature. The experiment shows that 24.0 joules of heat are needed. There's your Q, right? So you've got Q, you've got M, you've got delta T. The only thing left is C, right? So this is to find the heat capacity. What can the chemist report for the molar heat capacity of C3H9N? So notice how this is not asking for the specific heat capacity. It is asking for the molar heat capacity. And the two are related, but they're not exactly the same. But in its essence, this is the same kind of problem. Q equals MC delta T. We're trying to find out what C is. So let me talk a little bit about molar heat capacity. Okay. This, if it's written just as a C, it means specific heat capacity. And the units of the specific heat capacity are generally joules per gram let's use Kelvin, okay? We'll put in Kelvin instead of degrees C, right? Or joules per gram degrees C, write that way too. Sometimes we want to do it, instead of divided by grams, we want to do it divided by moles. And that's called the molar heat capacity. Okay. The molar heat capacity, we could write it this way. Well, I'll just write it this way. Put a little m down there. M for molar. And the units are going to be joules per mole Kelvin instead of degrees, instead of grams, or joules per mole degrees C. Okay. So it's per mole instead of per gram. So is that right? No, I'm sorry. I made one mistake here. It's not M, it's N. Where N is the number of moles. Okay. Yeah, there we go. Now it's right. So this is the number of moles, okay? So all we're doing is we're substituting moles for grams. So what does that mean? Think about it this way. I could have 18 grams of water, 18.02 grams of water, right? That would be a measure of how much water we have. I could also say that that corresponds to 17.95 milliliters of water. Okay, the density of water is a little less than 1 at room temperature. So the volume of water is not exactly equal to the mass of water. It's a little bit less, but those two numbers are pretty close, right? So back, if you did the calibration of volumetric glassware, you looked at that table 5 and you had all those densities of water that were a little less than 1. Here you go. So that would be a different way to measure how much water we have, right? We could do mass, we could do volume, we could also do moles. I could also say this water is a mole of water, right? In fact, these two are pretty directly connected through the molar mass, right? That's all you got to do. How are these two connected? These are connected by the density, right? So if you know the mass and you want to find the volume, you use the density. If you have the mass and you want to find the moles, you use the molar mass, right? So there are different ways of saying how much stuff you have. Now, in general, to say how much stuff you have, it depends on the context. So if I'm in a laboratory and I say, hey, get me some water, most likely you're going to ask for a volume of water. But if you're doing really, really precise measurements, you might actually ask for a mass. And then if you're doing calculations and you want high precision, you might use the number of moles. So here, all we got to do is just have the number of moles of water or the number of moles of substance, whatever the substance happens to be, okay? So molar heat capacity, Q equals N times C sub M for molar times delta T. So coming back to that problem, let's take a look at what it says. We know the change in temperature, we know the amount of heat, we know the mass, but we want to find the molar heat capacity. So that'd be C sub M. Notice how they give you the chemical formula of the substance. They have to give that to you, right? Because if you know the mass of something and you need the number of moles, you're going to need the chemical formula to find the number of moles, right? Because you got to find the molar mass. So that's why they tell you it's C3H9N. So let's take a look at this one. We've got all the numbers. It's just the molar heat capacity. So I'm going to write it this way. Well, let's put the numbers down first, and then we'll go through the calculation. So first of all, we know there's 610.0 milligrams. Okay, so that's your mass. And if we wanted the specific heat capacity, that's what we would do. We're also told that the amount of heat is 24.0 joules. So that's your Q. We're also told two temperatures, 0.2 degrees C to 14.1 degrees C. So that's a difference of 13.9, right? So you can either write it that way or 13.9 Kelvin, right? Delta T is the same in Celsius and Kelvin. Now, they tell us the chemical formula is C3H9N. Okay, so there's your chemical formula. That's going to allow us to find the number of moles because we can use the molar mass. Okay, and then now we can come back. We want to know C sub m. So I said it's N times C sub m times delta T. So C sub m is what we want. So Q over N delta T would be C sub m. Okay, so let's put everything in. We've got 20, so C sub m is 24 joules. But now we don't have the number of moles, so I'm going to put that in parentheses. We'll come back to it. And then our change in temperature is 13.9 Kelvin. Okay. Let's find the number of moles. 610 milligrams. Okay, so that's an issue. 610.0 milligrams of C3H9N. Okay. 3, 5, 7, 8. I think I figured it out. Okay. So now here's what we can do. This is milligrams. So 1 milligram is 1 times 10 to the minus 3 grams, right? 1 milligram, 1 milligram. Okay, so 610.0 milligrams, 1 times 10 to the minus 3 grams is a milligram. Milligrams are gone, and you get 0.610 grams. So there's your mass in grams. Okay, now we want to find the number of moles. This is moles. So now what do? We say 0.610 grams. Let's figure out the molar mass of C3H9N. There are 3 carbons. So 3 times 12.01, 9 hydrogens, 9 times 1.01, and then 1 times 14.01 for the nitrogen. So that's 36.03 plus 9.09 plus 14.01. So you're going to divide it by 59.13. Divide by molar mass to get moles. So 0.610 divided by 59.13, and you get 0.01032 moles of C3H9N. So now you can put that in there. 0.01032. That's moles. Sorry, I ran out of room there. So you got 24.0 divided by 0.01032 divided by 13.9, and you get, was it 167? To 3 sig figs, it's 167. The units are joules divided by moles divided by Kelvin. Sorry, that's so small. Okay, so notice the molar heat capacity is going to be larger than the specific heat capacity. If we were going to do the specific heat capacity, it would be 24.0 divided by 0.610 divided by 13.9, and you'd get 2.83. So your heat capacity is, I'm sorry, your specific heat capacity is 2.83 joules per gram degree, or gram Kelvin, I guess. And then your molar heat capacity is 167 joules per mole Kelvin, right? So you get a bigger number than you get with that one. So be careful. This sometimes comes up when you're online and you're looking up problems and you'll see, oh, here's the heat capacity for some substance. be careful, look at the units, because if it's the molar heat capacity, it's going to be a lot larger, or usually it's larger, a lot larger than the specific heat capacity. And the reason it's larger is because you're dividing by the moles. So if you're dividing by the moles are going to be smaller than the mass. The number will be smaller. And so if you're dividing by a smaller number, you're going to get a larger number. So you're going to get 2.83 instead of, I'm sorry, get 167 instead of 2.83. Okay. So again, that's very similar. So all 5 problems that we've done, is it 4 or 5? All 4 problems that we've done are very similar. They're all using that Q equals MC delta T. The difference here is that it's N for moles, C sub M for molar heat capacity, and then delta T. Okay. And we got one more to do here. I'm going to show the picture, if I can find it. Okay, here's our picture. Solving a basic calorimetry problem, a 51.1 gram sample of aluminum in a calorimeter. See the sketch at the right? So that looks like a constant pressure, right? It doesn't look like it's a bomb calorimeter. You don't have the electrical device in there, no wires. That's your basic constant pressure calorimeter. It contains 200 grams of water. The aluminum sample starts off at 93.3 degrees Celsius, and the temperature of water starts off at 15.0. When the temperature of the water stops changing, it is 18.7. Assume that the pressure remains constant. Calculate the specific heat capacity of the aluminum according to this experiment, okay? Now, this is an interesting problem because there are 2 materials that we're concerned with. The first one is the aluminum, and that's what we're trying to find the specific heat capacity for, right? The other one is the water. In fact, a lot of the information is about the water, right? It tells you the mass of the water, 200 grams. It tells you the temperature of the water at 15, and then it tells you the final temperature of the water, which is 18.7. But it also gives you the initial temperature of the aluminum. There's a lot of information in there. So how do we dissect this? The issue here is that energy is actually being transferred from one material to another. So here's what's happening. The aluminum, I just want to make sure this gets right, yeah. So what they're doing is they're taking a piece of aluminum, which is initially at 93.3 degrees Celsius. Okay, and I'm going to actually go ahead and write down some of the numbers here. It's 51, so the mass of the aluminum is 51.1 grams. Okay. We're trying to find the specific heat capacity, so we don't know that. Okay. We also aren't explicitly given T2, right? Because we realize, right? If you're given the mass, if you're given the initial temperature, the final temperature, and the amount of heat, you could find the specific heat capacity. But some of these things we're not given. We're not given Q. We're not given T2, at least not explicitly. So how do we go about this, right? Well, here's the other issue. There's also water involved. So there's also this cup of water. And so the water has information too. The first piece of information is that the water starts off at 15 degrees C. And then it ends at 18.7 degrees C. Okay, so we're told both the initial and the final temperature of the water. Then we also know, now it doesn't actually explicitly tell us this, but the specific heat of water is 4.18. Okay, which, you know, hey, that's just a number that you can look up. We know that value, right? Now, actually, you could look it up for aluminum too, but we don't want to do that for this one. And then the mass of the water is given at 200 grams. Okay. And yep, I think that's all the information. So there's all this information. So here's what's happening. You're taking the piece of aluminum, which is at a very high temperature, 93.3 degrees Celsius. You're dunking it into the water. You're putting it into this water bath. And so now it's over here. And then this is water. Okay. Now, initially the water is at 15 degrees C. So initially the temperature is 15 degrees C. Initially the aluminum is at 93.3 degrees C. So what direction is the heat going to flow when these two come into contact with each other? Is it going to, is heat going to flow into the aluminum from the water, or is heat going to flow from the aluminum into the water? That's the issue. The hotter object transfers its heat to the colder object. The water's colder. So that means heat is going to flow in this direction, right? Q is going to go from the aluminum into the water. And the question is, what happens? Does it can't keep going on forever, right? There's not an unlimited amount of heat. What happens is as heat flows into the water gets hotter. So the water goes up to 15.1, 15.2, 15.3, 15.4. The aluminum starts going down, 93.3, 92.3, 91.3, 90.3. Eventually, they reach the same temperature. And when they are at the same temperature, everything stops. The heat flow stops. There's no longer any heat transfer. So what that tells us is that the final temperature here is going to be the same as the final temperature here. They have the same final temperature, and they're telling us it's 18.7. Okay, so that's the key. A key step is that the final temperatures have to be equal to each other when you do a calorimetry problem. Okay, so if this were, if this were 103, the final temperature would be a little hotter. It might be around 19 degrees C. See how the water really didn't change that much? The water only changed a few degrees Celsius, whereas the aluminum went all the way from 93 down to 18. That's a big change. The reason for that is twofold. One is there's more water. The more water you put in there, the less it's going to change temperature, right? The same amount of heat will not have that much effect on a lot of water as it would as with a little water. The other issue is the specific heat capacity. The specific heat capacity of water is very large, 4.18. Metals are generally less than 1. When we do this problem, the aluminum is probably going to be around it's going to be less than 1. I forget what the actual value. Copper is 0.385. Gold is 0.129. Iron is 0.44 or 0.56, I think. It's going to be less than 1. It's probably around 0.3, 0.29 or something like that. But in any case, metals have much lower specific heat capacities. What that means is the same amount of heat will cause the temperature of a metal to change much more than it will for water. Water really, it takes a lot of heat to change the temperature of water. So you can actually use that to store energy. You put a lot of energy into water, it's still liquid water. Store a lot of energy in that way, right? Okay. The oceans store a lot of thermal energy. Now, what do we do? How do we solve this problem? Well, what we can say is this. Any heat that flows from the aluminum goes into the water, all right? So here's what I'm going to say. The heat that is lost by the aluminum, that's the amount that the aluminum is transferring into the water, plus the amount of heat that goes into the water, I'll put W for water, has got to be equal to 0, right? In other words, if the aluminum loses 30 joules, the water gains 30 joules. They have to be equal to each other. But what the difference between gaining and losing is the sign. Losing is negative, gaining is positive. So if this is minus 30 joules, this is going to be plus 30 joules, and the two of them added together will give you 0. So this is an important equation. This can be changed. We can write the QW on the other side. QAL equals negative QW, right? That's just another way of writing the same thing. You put the water on the other side, it's now negative. But adding a positive and a negative gives you 0 if the numbers are equal magnitude, okay? So why did I write it this second way? Because we want to know something about the aluminum. We don't want to know Q, but we do want to know C. So what I'm going to do is go through a little derivation for you here. Q aluminum equals minus Q water. MC delta T of the aluminum, AL, AL, AL equals minus M water, W, C, W, delta T, W. So we're substituting, right? This is an important thing we do in the sciences. Q is equal to MC delta T. So we're substituting in MC delta T for both the aluminum and the water. We know a lot of these values. We know the mass of the aluminum. We know the change in temperature of the aluminum. We know the mass of the water. We know the specific heat capacity of the water. We know the change in temperature of the water. The only one we don't know is the specific heat capacity of the aluminum. So here's what we do. Okay. I'm going to write this up here a little nicer. I have a little more room here. Mass of aluminum times specific heat of the aluminum times change in temperature of the aluminum equals minus mass of the water, specific heat of the water, delta T of the water. We want to know the specific heat capacity of the aluminum. So I am going to divide both sides by the mass of the aluminum and the delta T of the aluminum, the change in temperature of the aluminum. What happens? This divided by this is 1. This divided by this is 1. And you've got the specific heat capacity of the aluminum. So I'm just going to try to write this one more time. Don't forget this negative here. Mass of the water, specific heat of the water, change in temperature of the water, divided by mass of the aluminum, change in temperature of the aluminum. Okay? That's how we're going about it. So the trick here is to recognize two things. One, that heat is flowing from the aluminum to the water. So those two, the heat for each is going to be the same, just a different sign. By doing that, you can now substitute in this. And then you come back and you say, well, wait a minute. Q is equal to MC delta T. So I'm going to do MC delta T for both of them. Don't forget the negative that's on the right side of there. And then you've got that. The other trick is that they give you the final temperature of the water, but the final temperature of the water is going to be the same as the aluminum because that's when the heat transfer stops. Okay? So you're never actually calculating Q. You could. Another approach to this would be to figure out what Q is for the water and then figure out what, then that would be equal to negative Q for the aluminum, and then use the negative Q for the aluminum to find C of aluminum. You could do it that way too, but this is generally the way that I do it. Okay, so now it's just a matter of putting in the numbers. I'm not going to put in the units right here. I'm going to leave that for you to prove to yourself that the units do work out. The mass of the water is 200 grams. The specific heat of the water is 4.18. The change in the temperature of the water, for the water, it went from 15.0 to 18.7, so that's 3.7. Now we're going to divide that by the mass of the aluminum, which is 51.1. And then the change in temperature of the aluminum is negative. It went from 93.3 down to 18.7. So that's what, 19. So let's see, that would be 73.3, 74.6. So negative 74.6. Let me just check that just to make sure. 93.3 minus 18.7. Yes, negative 74.6, right? Remember, it's negative because you're going from 93.3 down to 18.7, okay? So now you have two negatives, one in the numerator, one in the denominator. Those negatives, for lack of a better word, would cancel. So you've got 200 times 4.18 times 3.7 divided by 51.1 divided by negative 74.6. Ooh. All right, I got to do it again because I made one mistake. 200 times 4.18 times 3.7 divided by 51.1 divided by 74.6. 0.81. Okay, so it's between 0 and 1. So if it's a metal, it's going to be less than 1. A 0.811. So there's your specific heat capacity of aluminum. The units are going to work out to joules per gram Kelvin. Okay, joules per gram Kelvin, which are the units we've been using all along. Okay, so it should be less than 1. So notice that specific heat capacity is much less than water. If you took 4.18 and divided by 0.811, you get a difference of 5.15. That means the specific heat capacity of water is more than 5 times that of aluminum. So the same amount of heat, you could do this little like kind of thought experiment. If I put in heat to make the temperature of water go up 1 degree Celsius, 20 to 21, the aluminum would go up 5 times as much. So water might go, from 20 up to 21, and then the aluminum would go from 20 to 25.1, right? 1.5, right? It goes up a lot more, right? That's only a difference of 4 degrees Celsius, but that's a big temperature change, right? A big difference between the two. And that's because of the specific heat capacities are so different, okay? Specific heat capacity is how much heat it takes to make 1 gram of a substance go up 1 Kelvin. And so there you go. So, all right, so that's it. Actually, all 5 of those calorimetry problems were very similar. They were all using your Q equals MC delta T. This one's just a little bit more advanced because you're transferring from one substance to another. But if you just, remind yourself that Q of one of the materials, I'll call it Q1, is equal to minus Q2, you'll be set, okay? That negative there, that's important. Don't forget that negative in there, because if you don't put that negative in there, then you get a negative temperature. And so you don't want to have that, okay? There you go. The last topic for chapter 5 is standard enthalpies of formation. So tomorrow, which is Thursday, we will cover the standard enthalpies of formation. So we'll go over that. And that's actually probably a relatively short topic. And so I'm just going to probably do an hour. It'll be a little bit shorter, but that should be done on Thursday. And then that will give you the weekend to work on preparing for the exam and finishing up all your topics here. The next one that we'll talk about on Monday is chapter 10. We'll start talking about gases. So we'll look at Kelvin scale, all the gas laws. Again, relatively simple arithmetic. It's fun stuff, proportionalities and all of that. But we'll work on gases next. And then gases is the last chapter before we start getting into the modern chemistry, which is quantum mechanics, wave mechanics, chemical bonding, all that fun stuff that we'll do toward the end. So we're headed out there. So hang in there, keep at it, keep working each day, and good luck. Take care.
Thank you so much.
Oops.